Good afternoon. You are welcome to the second stage of the facilitation for 2022 academic sessions. I'm Dr. Adetunji Bamidele Ibrahim from Best University of Technology, Ota. So I'll be in charge of phases 407 for the next 8 weeks. So I think I sent some mails 3 days ago where I sent the first one. I sent the course facilitation plan that, and also sent the second mail along with the course materials. So I believe each and every one of you now has his or her own details as regards to the course for this second stream. So today is more or less like an introduction to the course. So I'm going to give you the details of what we are going to be doing for the next 8 weeks and what you are expected to learn from this course. So as I've said in my first mail, that this course we'll be having the classes on Fridays between 4 to 5 p.m. Nigerian time. So please take your time and make sure you stick to the allotted time. So for the first week, it's just about the introduction to the course, what you're expected to learn from the course, and what you are expected from me. Specifically, for us to be able to have effective disseminations and interactions as regards to this course, periodically during the weeks, I'll be sending mails across giving you details information on what you need to do before our class on Friday. And also, you have the opportunity to reach out to me by mail or through WhatsApp if you have any questions you want to ask. So for this course, it's all about solid state physics 2. So we are going to be discussing dielectric properties of solid. From there, we also talk about the local electric field. We are going to define the concept of dielectric constant, explain the basic theories and the equation connecting dielectric constant with pulsability and susceptibility and their uses, while we also try to look at what is called magnetization of in materials. Magnetic properties play a lot of roles in day-to-day activities of devices that we use. So we are going to be looking at some of the materials that have magnetic properties and how to identify which of the magnetic properties each of these materials possesses. So also we are going to be discussing some basic types of magnetization or magnetic properties. We shall be talking about antiferromagnetic, ferromagnetism, diamagnetism, paramagnetism, and others like that. So in the last 2 weeks of the facilitations, which is the 7th and the 8th weeks, we are going to be discussing imperfections in solids. So here we shall be looking at the effect of impurity in crystals. So if you have any questions, you can ask. So I have break down all the courses into modules per week. So the second week of our lecture, which is going to be next week, we shall be discussing dielectric properties. What exactly are we going to cover here? We are going to cover mainly the properties of materials that has dielectrics in them. Solids, specifically. We're going to be discussing some solids and trying to understand the concept of dielectric in this solid. This also will span to the third week, where we are going to be looking at pulsability, dipole, relaxation, and dielectric losses in some of these materials. Like I said, in the fourth week, we shall be looking at magnetism. Then we consider the concept of magnetization, diamagnetism, paramagnetism, ferromagnetism, which are going to be discussed in details, and it also span to the fifth week. And in the sixth week, shall be looking at magnetic resonance. Here we are going to be discussing nuclear magnetic resonance, ferromagnetic resonance, and antiferromagnetic resonance. Their uses, the theory behind them, and how to link some of the connecting equations in this concept. So today, I will give you a brief introduction to dielectrics and some concepts about solid state physics. Okay, so we start with introduction. In year 3, I think you are familiar with the concept of solid state physics, which is majorly a branch of physics that deals with matters and solids. And we discuss this concept using the concept of quantum mechanics, along with the concept of crystallography and electromagnetism and metallurgy. So solid state physics is one of the branch of condensed matter physics, and solid materials are formed from densely packed atoms. So these densely packed atoms, they interact. So when they interact, these interactions give rises to series of properties. For example, mechanical properties, which has to do with the hardness, the softness, and the elasticity of this material. Also, when they interact in the presence of heat, this gives us the idea of thermal properties of the materials. How do they respond to thermal properties when they interact under the influence of temperature, heat? Also, electrical properties, then magnetic properties, then optical properties of solids. So all these one depend on condition with which these materials are formed. Most of the solid materials are arranged in a regular fashion, which is called crystalline solids. So some of these materials in this class are metals and ordinary water ice. Then we have others that are also irregular. So these ones are known as amorphous solids. An example is glass. So the question is that what is the importance of solid state physics? Solid state physics applies everywhere around us. Like I said some minutes ago, that most of the devices we are using today, they consist of some materials built from the concept of solid state physics. So it involves how the micro scale properties of solid materials results from their micro scale properties, that is from macro to micro. So most of the solids are arranged in such a way that their atoms are in an orderly repetitive array. So the solid you see around are examples of solid state physics, e.g., sugar molecules, then salt, which is sodium chloride, glass, and many more like that. So it forms the theoretical basis of material science. So there is no how you understand material properties without understanding the concept of solid physics, because it is the basis of material science that produces most of the electronic devices, appliances that we use today. Its applications are in technologies of transistors and semiconductors. Most of the transistors we use in electronic industry and semiconductor industries are basically derived from the concept of solid state physics. Then if you want to discuss this quantitatively, you need to understand the concept of quantum mechanics and electromagnetism, also crystallography concept. So the modules in this course are divided into 3 units, which is module 1 with unit 1, unit 2, unit 3. Dielectric properties for unit 1, magnetism for unit 2, and imperfections in solids for unit 3. So a very good textbook for this course is Introduction to Solid State Physics, which is written by Charles Kittel. You can also look for Archtroff. This is also a very good textbook in solid state physics. So in this course, you are going to be assessed using 2 concepts. The first one is through self-assessment exercises and tutor mark assessment. So it's going to be a continuous form, and most time you are expected to do most of these things on your own. If you have problem, you ask questions, then we look at it together and find a lasting solution to it. So for today, we start the dielectric property, which is unit 1 of solids. So when you talk about dielectric properties of solid, it said solid state is the study of crystalline solid through methods such as quantum mechanics, crystallography, electromagnetism, and metallurgy. It is the largest branch of condensed matter physics. So how the large scale properties of solid material is solved from the atomic scale properties. Thus, solid state physics form the theoretical basis. I've explained this some minutes ago. Now, there is no how you discuss the solid materials without looking at some of the properties associated with them. So we said solid material can be divided into two distinct groups on the basis of their behavior under the influence of external electric field. One of the properties is conductor, those in which there are electrons which are free to move in the presence of a field. That those are the one referred to as conductor. An example of these are metals and carbon, etc. like that. Then we have insulator or dielectrics, those in which the electrons are strongly bound to atom or molecule composing the material and cannot be detached by the application of electric field to this material. Example of these are sulfur, proclaim, mica, and etc. like that. These are insulators because they are different from conductor. They are bound together by electrons, which are strongly bound to the atoms and the molecules of the material that consists them. So the question now is, what is dielectric properties? A dielectric is a non-conducting material, such as glass, rubber, or waxed paper. So the following are some of the properties of dielectric. One, when a dielectric material is inserted between the plates of a capacitor, the capacitance increases by a factor K, called the dielectric constant of the dielectrics, which is written mathematically in equation 1.1, and C is equals to K C naught. So C naught here is the capacitance that is in the absence of the dielectrics. Then two, the dielectric constant K has no unit, and it is characteristics of a given material. That is, it depends on each material, different material with different dielectric constants. It is not uniform, it is material dependent. The dielectric constant for a silicon material is different from dielectric constant for a magnesium selenide semiconductor. So it is materials dependent. Three now, if epsilon naught is the permittivity of free space and epsilon is the permittivity of the dielectric material, then we can relate these two together using the dielectric constant approach. So K is now equals to the ratio of the permittivities of the dielectric materials and the permittivities of a free space. So if you look at equation 1.2 and equation 1.1, we can actually relate these two equations together based on the constant called dielectric constant. So another important properties is introduced in 1.3, which is the the energy densities that is being derived from the dielectric materials. U is equals to half epsilon E squared. E here is electric field. Now, the potential difference V between the plates when a dielectric material is inserted or provided that the charge remains unchanged is given as. So here we find a way to relate the potential difference between the plates when a dielectric material is inserted with respect to dielectric constant. So that gives us V is equal to V naught over K. So V naught here is the potential difference when dielectric is not inserted, while V is the potential difference when V is inserted, when you introduce electric field into the system. So which gives us equation 1.4. So equation 1.4 states that the potential difference V between the plate decreases by a factor of K. So if the potential difference is kept unchanged, that is, the potential difference is uniform, when the dielectric material is inserted, then we can write this equation in terms of the charge that flows through in the field. So we can say that Q is equals to Q naught. So thus, the charge on the capacitor with a fixed potential difference between the plate is increased by a factors of K. Also, if the electric field between the parallel plate capacitor is E naught and it is E after the material with dielectric constant K is inserted. So you see that you generate another E when you now put in dielectric material in the space between the plate. Then we can also write an expression which is given in equation 1.6 as E is equal to E naught over K. You can see that we are trying to relate most of these properties: electric field, charge, potential difference, permittivities of free space, capacitance of a capacitor with respect to a constant called dielectrics. So from equation 1.6, we see that the electric field within the dielectrics is reduced by a factor equals to the dielectric constant. With this, now we can write what we call the net E, that is the net electric field. So the net electric field within the dielectrics is given by E is equals to E naught minus E naught minus EIND. EIND means induced electric field. That is, E naught is the electric field in the absence of is the electric field inside of the dielectric, but by the time you introduce dielectric, you have induced the field, you have a different electric field. So where E naught is the original field and En is the electric field induced. So if you combine all these equations together, you can derive an expression which is written in equation 1.8. So the induced electric field in the dielectric is related to the induced charge density, sigma IND. Through the relationship, you have this, that is the induced electric field is equal to the charge induced divided by epsilon naught, that is the permittivity of the free space. So if you combine this together, you now have equation 1.9 and equation 1.10. So since K is always greater than 1, these expressions, equation 1.8, 1.9, and 1.10 shows that the induced electric field is greater than the electric field without dielectrics, and sigma induced, which is going to be greater than sigma, and charge induced, which is going to be greater than the charge. So I think we are going to stop there today. If you have any questions, you're free to ask. So I'm expecting questions. Okay. So in the absence of no questions, I think we call it a day today. Then we meet next week by the same time. Please stick to the time and join us as early as possible. So in the course of the week, if you have any problem or any questions, you can always reach out to me by email or you send a WhatsApp message to me. So thank you for coming. So see you next week. Have a nice and lovely weekend.